In this module, we are going to be talking about infinite limits. There are of two types, in fact, four types, but let's restrict ourselves to two types. When x approaches infinity and when f of x goes to infinity. So let's make this precise. First, let me introduce some new types of intervals. Consider, so let's definition. Let a be a real number. We define open A infinity to be the set of all x in R such that x is greater than A. Then we define the interval minus infinity A to be by definition equal to x in R such that x is less than A. Okay. Then we define closed A infinity to be the interval x in R such that x is greater than or equal to A. Then minus infinity comma A closed here, this is just x in R such that x is less than or equal to A. And finally minus infinity open is just R. Okay. Now we are just defining various intervals that have the symbols infinity and minus infinity. So let's make a remark. Infinity and minus infinity above are just notations. Okay, let me put this in red. They are not real numbers. Okay, in particular, it doesn't make sense in this course to talk about the set minus infinity A, for instance. That simply doesn't make sense. They are just symbols. And it doesn't make sense to ask what is infinity minus infinity or what is infinity by infinity, because we are not treating them as real numbers. They are just a convenient notation that will enable us to talk more freely about infinite limits. Okay, so there are several definitions we'll have to make. So first, let's make the definition of a set having arbitrarily large elements. So definition. Let S be a non-empty subset of R. We say S has elements that are arbitrarily large if for each natural number n in n we can find x in S such that x is greater than n. So no matter what large natural number we choose, we can find some element x in the set S that is even larger. Okay. Similarly, we say S has arbitrarily large negative numbers if for each n in n we can find x in S such that x is less than minus n. Okay, so you can find elements that are as large as you desire but negative. So these are very nice formalizations of the intuitive notion of a set being arbitrarily large and arbitrarily small. Okay, now we are going to try to define what it means for limit x going to infinity f of x to be equal to L. Okay, that's the aim. So definition. So let me just erase this definition. Let S be a set that contains, that is arbitrarily, that that contains elements that are arbitrarily large. Elements that are arbitrarily large. Arbitrarily large. Let f from S to R be a function and L be an element of R. We say limit x going to infinity f of x equal to L if for each epsilon greater than 0 we can find capital N in N such that if x greater than N and x is in S, mod f of x minus L is less than epsilon. The definition is a very parallel definition to that of finite limits. In the case of finite limits, you add x approaching a limit point. Here you have x approaching infinity. So all you say is for each epsilon greater than 0, we can find n in N such that if x is greater than N and x is in S, mod f of x minus L is less than epsilon. Remark. If f is from N to R, then f is a sequence, right? F is a sequence. Show that the above definition coincides with that of sequence convergence. So this definition is certainly an extension of what we have already seen for sequences, but except now this set S could be a very arbitrary set, not just natural numbers. Okay, so I leave it to you to define exercise. Define limit x going to minus infinity of f of x equal to L. Well, that's exactly the same analogous definition that you will have to make. Okay, so this deals with what happens when x becomes large. Okay, so example. So let me use a different color. Example. Limit x going to infinity of 1 by x is 0. Okay, so 1 by x is of course defined on R set minus 0 to R. Okay, how do you solve this? Well, fix epsilon greater than 0, choose n in N such that 1 by N is strictly less than epsilon. Then if x is greater than N, 1 by x is less than epsilon, and we are done. So this was a fairly trivial proof. We have now shown that as limit x goes to infinity, 1 by x goes to 0. Similarly, limit x going to minus infinity of 1 by x, this also converges to 0. Okay, x going to minus infinity doesn't change the behavior. 1 by x still goes to 0, not to minus 0, which makes no sense. Okay, now we come to the second definition. Let f from S to R and A in S be a limit point. We say we say we say limit x going to a f of x equals plus infinity if for each n in n we can find delta greater than 0 such that if 0 less than mod x minus a less than delta and x coming from S, we have mod f of x is greater than n. Okay. In other words, let's make a remark. This definition is fairly easy, but this remark is nice and expressive. In other words, f can be made arbitrarily large for x sufficiently close to the point A. So I'm not even going to bother trying to define precisely what arbitrarily large is. From the way this definition is phrased, it should be clear to you what it means. So we have now defined what it means for limit x going to a f of x to be infinity. Similarly, we can define limit x going to a f of x equal to minus infinity. The definition is exactly analogous. Okay, so again example limit x going to 0 of 1 by x is infinity. Okay, now is this correct? First of all, let's think about it. What happens when you approach x from the left hand side? Well, x blows up, 1 by x blows up, but 1 by x blows up negatively. So here I have to specify 1 by x is defined from 0 infinity to r. I can get away with this by redefining 1 by x to be only on the positive numbers. Now this is fairly easy to show, so I'm going to skip the proof. And leave you to do it. This is fairly straightforward. Okay. Similarly, limit x going to 0, 1 by x is minus infinity. Then 1 by x is defined from minus infinity 0 to r. Okay. That proof is also entirely similar. So final definition, and this I'm going to use the full force of language. So let f from S to R, where S contains elements that are arbitrarily large, we say limit x going to infinity f of x equal to infinity if f of x can be made arbitrarily large by making x arbitrarily large, So I'm using the full force of the language that we have developed to define this. I leave it to you to make this mathematically precise by getting rid of these words arbitrarily large and so on. Actually, it really doesn't matter. If you understand what it means mathematically, that's more than sufficient. So now we have extended the notion of limits to involve various infinite quantities. Similarly, I leave it to you to do it for minus infinity and various combinations that may have been left out. let me just prove one theorem. There are various limit laws that we have shown, right? And many of them do generalize when we have infinite limits. You can look through the exercises and solve them to see which of these go through. I'm just going to prove one of them. Okay, let S be a set and A a limit point, and let A be a limit point. Let f comma g from S to R. Suppose limit x going to a, f of x equal to L, and limit x going to a, g of x is equal to infinity. Then limit x going to a, f of x, g of x is also infinity. So if you have one limit going to infinity and the other limit going to a finite quantity, then the product limit goes to plus infinity. Now you should be a bit careful. This result is valid, but what will happen if f of x goes to 0, right? So L is not 0. We have to assume that L is not 0. If L is 0, you cannot really predict what is happening. So look through the exercises for careful statements of other limit laws. So proof. This particular limit law does require L not to be 0. Proof. Choose. So fix. We have to ultimately show that product is infinity. So fix n in n. Now choose delta greater than 0 such that, first of all, mod fx minus L is less than L by 2 if 0 less than mod x minus a is less than delta and x is in S, first of all. And second, mod g of x greater than 2n by L if 0 less than whatever, the same thing. So choose delta such that both these conditions happen. This can be done because you can choose delta such that the first condition is true. You can choose delta such that the second condition is true. Therefore, you can choose a delta that is the minimum of both such that both conditions are satisfied. Okay. Now, the first condition immediately gives that mod fx is greater than L by 2. Okay. It's greater than L by 2. Fine. So again, L not equal to 0 and L greater than 0. That's a better condition. Okay. F of x equal to L greater than 0. That is required. Okay. Excellent. We have both these. So because mod f of x is greater than L by 2 and mod g of x is greater than 2n by L, mod f of x g of x, g of x is simply greater than n if 0 less than mod x minus a less than delta and x is in S. Okay, this is an immediate consequence, hence proved. So if you have one quantity converging to a positive number and another quantity converging to infinity, then the product will have to also converge to infinity. Okay. So this concludes this module. Please do look through the exercises for many other limit laws involving infinite quantity. This is a course on real analysis and you have just watched the module on infinite limits.